This is your online module on statistical distributions. At the end of this module, you will be able to describe the graphical and mathematical properties of a statistical distribution, distinguish between continuous and discrete statistical distributions, identify some common statistical distributions used in engineering work. A little bit of a recap from our previous online module. Remember that random processes result in outcomes, which we record through different trials of the random process and deriving data. So, but how do we model a random process? We need to get familiarized with the concept of a random variable, which basically is the way how you model an outcome from a random process. There are different types of random variables, so in order to understand them, let's get familiarized with a little bit of nomenclature. So we use capital letters to denote random variable, just like in this case we're using X, and then we use lowercase letters for a specific value of the random variable. It denotes I because it's one of the options in the outcome space in particular. So going back to the different types of random variables, we can have a limited number of outcomes in the outcome space. When the outcome space is finite, like in this case, we have a dice that we roll and we have 6 possible outcomes, then we have a discrete random variable. And we can describe, for example, the probability of getting the value of that random variable to be exactly equal to 3. And that will correspond to this, the description of this type of variable. On the other hand, if we have an infinite number of outcomes within a specific range, for example, in this case, we are measuring height of some group, and we have that it ranges from 4 to 7 feet, not inclusive. But because it's a range, then we can assume that we can take any value in between, for example, 4.5, 6.75, etc. So in that case, then the possibilities in between those numbers are infinite. Therefore, these are considered continuous random variables. And we describe those probabilities of a random variable based on intervals from certain values. So from here we need to describe what is a probability distribution. A probability distribution reflects all possible outcomes of a random variable and their associated probabilities, and it can be represented in a tabular form or in a graphical form, like we will see it in a minute. But it has different characteristics. In particular, that the outcomes listed must be disjoint, which means like they do not overlap, of course, and they are ideally extensive, or it counts for all of them. And then that each probability must be between 0 and 1, and of course the sum of all of them should be equal to 1. Let's see a little example here. It is talking about a statistics class assigned to textbook, one textbook and its corresponding study guide. So the university bookstore has determined that 20% of enrolled students do not buy either book, 55% buy the book only, and 25% buy both books. So they also found that these percentages are relatively constant from one term to the other. And we get 100 students. We want to know how many books should the bookstore expect to sell to this class. So the probability distribution will be represented graphically in the following way, because we have the different values of the number of books, and we have probabilities for each of them, like how many, what probability do we have for people to get the number of books. So then we calculate 100 times that particular class, 0, 55, or 25, and we multiply by the actual value for that for those possibilities in the random variable number of books. So the expected value for that will be 105. Then an extension of this, let's say like the textbook cost $137 and the study guide costs $33. How much revenue should the bookstore expect from this class of 100 students? So again, let's remember that the random variable is denoted by a capital letter, and one specific value within that random variable is a lowercase letter. Then we have 1, 2, 3 possible values, 0, 137, and 170, and the probabilities for each of them. So now if we plot cost, you see that now the possibilities are like way apart, and but each still have particular heights related to their probabilities. So if we do the same type of calculation than before, then we calculate the probability times the number of people that I have and times the value for each of the classes. So this is the amount of profit that the bookstore could expect. So as you can see, it's not trivial. Is the calculation of an expected value and such is depending on the particular distribution of a probability distribution and the values on them. So it might be time consuming if we don't have a shortcut for it. So we're going to talk about that in a minute. So other options of random variables, of course, now these are continuous random variables, and this is going back to the example of height, right? So we have histogram, which is having really wide bins in here, and then it starts narrowing here, and then on the bottom we have even narrow bars and narrower. So on the one on the right, you can see that we can denote certain bars and actually ask about what is the probability of having people in between these ranges, right? Because those are the ones that are illuminated here. So given that bin size, then we could calculate this this probability by summing the height of these two bars. So more in discrete probability distributions, so we call the probability distribution in different ways depending if they are discrete random variables or if they are continuous random variables. If we have discrete random variables, we call it probability mass function. So you can see here on the y-axis you have fx, which is probability, and then all the possible values on the x-axis, and here are the three characteristics that we saw before, but with another language, right? So the characteristics of this function is that it's always positive, it always goes to the right, and then that the sum of all of those values will get to 1. So all the sum of these little bars will sum up to 1, and that the specific function at a particular x value will give me the probability of the random variable being equal to that specific value. So if we move to the continuous version of it, we still have that the function will always be positive and moving to the right, but now because it's continuous, we have that what captures the whole probability is the actual integral of the function from the beginning till the end. So we just denote it as minus infinity to infinity, of course. And if we want to calculate the value of a particular interval, then we will need to calculate that integral between the limits a and b that we defined. It's important to notice that when we're talking about continuous random variables, because it's all now smooth and continuous, then a specific point, it doesn't make any sense for us to actually ask for a specific point, like what is the probability of a being equals to, of x being equals to a in particular. That will be 0 because the probability of a particular point doesn't exist. the probability of a range of points does exist because it's calculated through calculus. So the nomenclature for probability distributions of continuous random variables is to call them probability density functions, or PDFs. So from here, I just want to reinstate that probability distributions are statistical distributions. They are just synonyms of them. So, but I wanted to make it particularly clear that we were talking about probabilities and how probability play a role into building it and interpreting it. So from there, now that we know all those details about probability distributions, we can think about the benefits of using them now once you know the distribution of a random variable. So the main one is that you can calculate those theoretical probabilities of interest, of course, but also that instead of having to calculate all those integrals and such, you can calculate mean and standard deviation from simple formulas. And it supports also the process of inferential statistics. If you know that the random variable distributes in a certain way, then you can definitely make more solid inferential statistics in the future. So from there, let me walk you a bit about the many statistical distributions that you can work with. So on the left, you have the continuous distributions. On the right, you have the discrete distributions. And we're going to be talking a bit about each of them. I put those relationships because sometimes some discrete distributions in certain conditions may approximate continuous distributions, as well as some continuous and discrete distributions complement each other. The first one is the Bernoulli distribution. So a Bernoulli random variable is basically one that can take between the values of 0 or 1. And it takes the value of 1 with probability p, and the value of 0 with probability 1 minus p. So you can see that there is the graph. This is the graph of the probability distribution. And for short, we will be calculating the mean of that distribution to be equals to p, as well as the standard deviation to be equals to this form. The next discrete distribution is binomial. So the binomial distribution basically tries to model the number of successes in an X number of trials. So for example, if I have 6 trials, it describes the probability of getting 0, 1, 2, 3, 4, 5, and 6 successes from all those trials. So one particular characteristic of this is that when n and p, n times p and n times 1 minus p are greater than 10, this distribution approximates to normal, and that is really convenient for many reasons. So here is a statement of the approximation to the normal by the binomial distribution, and you can see these histograms actually show how if you have an n which is like limited, like really small, like 10, this really doesn't show any normality or symmetry of any sorts. But as long as you keep moving on the sample size, then the distribution keeps shaping and resembling a normal distribution, quite symmetric. Then another discrete distribution is the geometric. This one is used to describe how many trials it takes to observe a success. So basically, it's kind of mapping how many trials I will need to get my first success, and it's related to the Bernoulli experiments and the binomial distribution too. So we have our particular formulas to calculate their mean and standard deviation. Another one is the negative binomial. This one describes the probability of observing k successes on the nth trial. So for example, if I have 5 trials, then the probability of observing 0 successes, or 1 success, 2 success, 3 success, etc., till that trial. And then another discrete distribution, one which is really relevant, is the Poisson distribution. This one is estimates the number of events that happen per unit of time. So for example, let's say that you are counting heart attacks in a population, or getting married within a population, getting struck by lightning, or even the number of customers that come into a shop for a certain period of time. So we calculate the probability of observing a certain number of events k through this formula, which includes lambda, which is a rate that we will use. So, and then from there we swap to continuous distributions, and one that goes actually hand to hand with the discrete distribution of a Poisson is the exponential, because the exponential distribution actually talks about the length of time between occurrences of events. So basically they are complementary in the sense that the Poisson counts the number of events, and then exponential considers the length in between those events. As you see, you always you again see the lambda factor here. So then the queen of all distributions, the normal, it's unimodal, is symmetric, is bell-shaped, and many variables are close to normal, even though not all of them are exactly normal. And we denote it as with this description. You know, a random variable is said to be normal with certain mu and sigma, and we denote it by writing it this way. From there are certain others that are useful for engineering work. For example, the Weibull distribution is useful to model time until failure of certain physical systems. So here we have the probability distribution, and we have the way to calculate mu based on those parameters and such, as well as the standard deviation or variance. Same thing with the log normal. It has a particular set of parameters, and we have a way to calculate its expected distribution, its expected value, and the variance. Finally, the gamma distribution is quite complex because it has a variety of parameters to change, and depending the parameters, of course, the shape that it will have. And here is the short version of their mean and standard deviation or variance. All of these have particular applications in reliability studies and other engineering applications. So finally, when we have a gamma distribution with lambda equals to a half, and r in terms of in halves or integers, then we have a chi-square, and the chi-square is quite particular and useful in this course. So we're going to talk about that a bit later. So finally, let me wrap this up with the different relationships that you can expect between the different distributions. And for example, the relationship I mentioned between the binomial and the normal is denoted by this arrow here, and there are many others between the other types of discrete variables. Similarly, with the continuous variables, here in the center is the normal, but we also have the gamma, the chi-square, the exponential that we talked about, and the such. So this is your time to practice. This is a reminder of your learning objectives. Check your understanding through taking the quiz.